This presentation is delivered by the Stanford Center for Professional Development.
Okay, so welcome back. What I want to do today is talk about really one of my favorite algorithms for controlling MDPs that I think is one of the more elegant and efficient and powerful algorithms I know of. So concretely, what I'll do is first start by talking about a couple of different variations of MDPs that are slightly different from the MDP definition you've seen so far. These are sort of pretty common variations. One is state action rewards and the other is finite horizon MDPs. And then using this sort of slightly modified definition of an MDP, I'll talk about linear dynamical systems. Spend a lot of time talking about models for linear dynamical systems, and then talk about LQR, or linear quadratic regulation control, which will lead us to something called the Riccati equation, which is something we will solve in order to do LQR, linear quadratic regulation control. So just to recap, right, and you've seen this definition many times now, we've been defining an MDP as this tuple right? States, actions, state transition probabilities, discount factor, and reward function, where, let's see, gamma, the discount factor, is a number between 0 and 1, and R, the reward function, was a function mapping from the states to the rewards, was a function mapping from the states to the real numbers, and so we had value iteration, which would do this. Right? And so after a while, value iteration will cause V to converge to V star. And then having found the optimal value function, you compute the optimal policy by taking essentially the argmax of this equation above. Right? Argmax over A of that thing. Okay. So in value iteration, as you iteratively perform this update, the function V will it will asymptotically converge to V star, right? So there won't be, so after a finite number of iterations, you get closer and closer and closer and closer to V star. This will actually converge geometrically quickly or exponentially quickly to V star, but you won't ever exactly converge to V star in a finite number of iterations. So what I want to do now is describe a couple of common variations of MDPs that will use slightly different definitions of first the reward function, and then second we'll do something slightly different from discounting, and then remember in the last lecture I said that for infinite state or continuous state MDPs we couldn't apply the most straightforward version of value iteration, because if you have a continuous state MDP, we needed to use some approximations to the optimal value function. It turns out later in this lecture, I'll talk about a special case of MDPs where you can actually represent the value function exactly, even if you have an infinite state space, or even if you have a continuous state space. And I'll actually do that to talk about these special classes of infinite state MDPs using this new variation of the reward function and the alternative to discounting, since that'll make the formulation a bit easier. Okay. So the first, sort of variation I want to talk about is state action rewards. And so I'm going to change the definition of the reward function, and this it turns out won't be a huge deal. And in particular, I'll change the reward function to be a function mapping from a state action pair to the real numbers. And what I mean by this is just the following. So you start off in some state S0, right? You take an action A0. As a result of your state and action choice, you transition to some new state S1. You take some action A1. You transition to some new state S2. You take some action A2. and so on. Right? So it's a state action sequence that you see. So in an MDP where you have a state action reward, your total payoff is now defined as this, where your reward function is now a function both of the current state and of the action you took in the current state. And so this is my, I guess, total payoff. And then as usual, my goal will be to find a policy, to find a function mapping from the states to actions, so that when I execute that policy, I can maximize the expected value of my total payoff. Okay, so this definition, it actually turns out that given an MDP with state action rewards, you can actually, so by filling with the definitions of the states, you can actually reduce this back to an MDP with only rewards that functions of states. That may or may not be obvious to you. Don't worry if it isn't. But using state action rewards allows you to more directly model problems in which different actions may have different costs. So our running example is that robot. And so if you have a robot and it's more costly for the robot to move than for it to stay still, right? Then you may give a robot an action to stay still, and the action to stay still may have a lower cost because you're not using a battery power, whereas if you move, you may charge it for that action. Another example would be, well, actually another navigation example would be if you if you have an outdoor vehicle, you need to drive over some sort of outdoor terrain. Then certain pieces of terrain, like very rough rocks or driving over grass, may be more costly or may be more difficult than driving over, say, a paved road. And so you may assign an action that requires driving over grass or driving over rocks to be more costly than driving over paved road. Okay. Cool. So this really isn't a huge change to the definition in MDP, and I won't really bother to justify this a lot, but Bellman's equations is sort of generalized in the way that you probably expect, in which V star of S is now equal to that. So previously, when the reward function was just a function of the state S, we could take the max and push it in here. But now that the reward is a function of the action you're taking as well, the max comes outside. And so this says that your expected total payoff starting from a state S executing the optimal policy is equal to first your immediate reward, RFSA, for executing some action A in state S, then plus gamma times your future expected total payoff. And and so this is your expected total payoff if you take the action A from the current state. And so, well, V star is the optimal value function. So your actual optimal expected total payoff is the max over all actions of this thing on the right. Let's see, value iteration, which I'm abbreviating VI. So value iteration, VI, is really the same algorithm. V of S gets updated as max over A, R of SA, really same thing. Just letting the right-hand side of Bellman's equations be just updating V of S using Bellman's equations. Again, you get value iteration in exactly the same way. And then finally, having found the optimal value function V star using, say, the value iteration algorithm, you can then compute the optimal policy pi star of S as same as before, really. Right. The best action to take in the state S is the action A that maximizes this thing on the right-hand side. So. Okay. So having used value iteration to compute the optimal policy, to compute the optimal value function, you can then find pi star using that. Okay. All right. So this is the easier of the two variations of MDPs I want to talk about. Let's talk about the other one now. Other questions? Actually, are there other questions about this? Okay, cool. So the other variation, the other alternative definition will be finite horizon MDPs. Right? And so finite horizon MDP comprises of 5 tuple SA state transition probabilities and the parameter T and the reward function, where here T is a parameter called the horizon time. And concretely, what this really means is that we'll be taking actions in the MDP only for a total of capital T time steps, right? So we won't use discounting anymore. Sorry, that's my. Okay. So in some state S0, take action A0, get to some other state S1, take action A1, and so on. And eventually you get to some state ST, AT after T time steps. And so my total payoff now will be given by this sum from time 0 up to time T of my sum of rewards. Okay? And so in other words, and my goal as usual, okay, so this is my total payoff. My goal as usual is to maximize the expected value of my total payoff. And I want to come up with a policy to maximize the expected value of this total payoff. The key difference is that the world only will exist, if you want, for T time steps, and after that there are no more rewards to be collected. So this turns out to be a more significant difference because it turns out that the optimal policy may be non-stationary. Okay. And the term stationary means that it doesn't depend on time, and non-stationary means that it may depend on time. So non-stationary roughly means that my optimal action to take will be different for different time steps. That's what non-stationary means. And just as a concrete example of that, as usual, imagine that we have some robot, and let's say the robot is here, and let's say that there's a grid cell over there with a +1 reward, and much further away there's a +10 reward, right? And so depending on how much time you have left on the clock, it may be better to go after the +1 or the +10 reward. So if it's still early in the game, you still have a lot of time, it may be better to head towards the +10 reward to try to get a much larger reward. Whereas if you only have a couple of time sets left, if the clock has nearly reached the time capital T, then you may not have enough time to get to the +10 reward, and you may be better off heading for the +1 reward that's much more close by. So what this example illustrates is that when you're in that state, the best action to take could be to go left or to go right, depending on what time it is. And so this is an example illustrating how the optimal policy can be non-stationary. Okay. So, in fact, since we have non-stationary policies anyway, in the sequel, and then what I'm going to do next, I'm actually going to allow non-stationary transition probabilities as well. So, well, let me just write that up there. Concretely, what I mean is that so far I've been assuming that the state ST+1 is drawn from the state transition probabilities indexed by, the previous state and the previous action, and I've been assuming that these state transition probabilities are the same for all time steps, right? So long as you're in some state and take some action, the distribution over the next state doesn't matter. It doesn't depend on time. So I'm going to allow a slightly more general definition as well, in which we have non-stationary state transition probabilities, so that the chance over where you end up next may also depend on what time it is. Okay, so as some concrete examples of this formalism of non-stationary state transition probabilities, one example would be if you model flying an aircraft over a long distance. Then as the aircraft flies, you burn fuel and become lighter, and so the dynamics of an aircraft can actually change over time. Right? The mass of an aircraft can change significantly over time as you burn fuel, and so depending on what time it is, the dynamics or your next state can actually depend not only on your current state and your action, but also on how much fuel you burn, therefore what time it is. Other examples, actually another aerospace one is if you have the weather forecast for the next 24 hours, say, you know what the winds and precipitation and so on are going to be like over the next 24 hours. Then again, if you fly an aircraft from, say, here to New York, it may cost different amounts to fly different routes at different times, because maybe flying over the Rockies may cost different amounts depending on whether you do it now when there's really great weather, or if you do it a few hours from now when the weather may be forecast to be really bad. Or for a more example you see every day, same thing for traffic, right? And here, I guess at least, depending on where you live, certainly here in California, the times of day where traffic is really bad in lots of places, and so the cost to drive on certain roads may vary depending on what time of day it is. Lots of other examples. Industrial automation, different machines in a factory may be available to different degrees at different times of day. It may cost different amounts to hire different workers depending on when you need pay overtime for going late at night or whatever. So the cost of doing different things in the factory can also be a function of time. Excuse me, the state transition probabilities can also be a function of time. And lastly, while we're doing this as well, to make this fully general, we might as well have non-stationary rewards as well, where you might also index the reward function with these time superscripts, okay? Where again, the cost of doing different things may depend on the time as well. Actually, there's actually many more examples, non-stationary MDPs. So now we have a non-stationary policy. Let's talk about an algorithm to actually try to find the optimal policy. So let me define the following. Let's define. This is now a slightly modified definition of the optimal value function. Let's just write this down, I guess. And then sort of given okay. So I'm going to define the optimal value function, and now this is going to be indexed by t with a subscript t. The optimal value of a state, for time t, I'm going to define as your optimal sum of rewards for if you start the MDP at that state s, and if the clock starts off at time lowercase t. Okay, so the optimal value of a state will depend on what time it is and how much time you have left to run in this MDP. Does this make sense? And therefore, the sum on the right sums only from time t plus 1, time t plus 2, up to time capital T. And right, just stated in English again, this is your expected or your optimal expected total payoff if you start your system in a state S, and if the clock is already at time lowercase t. So it turns out then there's you can write out value iteration. You can write out Bellman's equations as well, but let me just write out the value iteration algorithm for this. It turns out you can, well, let me just write this out. Let's see, write this below. So it turns out you can compute the optimal value function for the MDP using the following recursion, which is very similar to what we had for value iteration. We're going to set V of S to be equal to max over A, same as before, right? Okay, so if I start the clock at time t and from some state s, my expected total payoff is equal to the max of all actions I might take of my immediate reward for taking that action in that state s, and then plus my expected future payoff. So if I take an action A, I would transition with transition probabilities P subscript SA S prime to some new state S prime. And if I get to the state S prime, my total expected payoff from the state S prime will be V star now subscript T plus 1 of S prime. And this subscript T plus 1 reflects that after I've taken one action, my clock will have advanced from time T to time T plus 1. And so this is now V star subscript T plus 1. Right? So this expresses V star of T in terms of V star T plus 1. And then lastly, to start off this recursion, you would have V star capital T of S is equal to right, it's just equal to that, because if you're already at time capital T, then you just get to take one action and then the clock runs out. And so this is V star capital T, your value of starting in some state S with no time, with just one time step, with no time left on the clock. And so in the case of finite horizon MDP, this actually gives us a very nice dynamic programming algorithm in which you can start off by computing V star of T, is this, and then you use this backward recursion to compute V star of capital T minus 1, capital T minus 2, and so on. You compute V star of T and T minus 1 and so on. You recurse backwards until you've computed V star for all of your time steps. And then, see this board? Can you see this board? Okay, cool. And then the final step is, well, previously we said that pi star of S, I'm going to come back and change this a bit, was the argmax over actions A of, R of SA plus sum over S prime, PSA, S prime. Right, this is sort of what we had. And in the finite horizon case, the optimal action may depend on what time it is. And so the optimal action to take at time T is argmax over actions A, that. Okay, and this is basically the argmax of exactly the same thing on the right-hand side as we had in our dynamic programming algorithm. And so you do this for every time steps, and now you've computed your optimal policy for different time steps. And again, note that this is a non-stationary policy because pi star of S may depend on what time it is. Okay. So one minor difference between this and the earlier version of value iteration is that, so what you do is you compute V star of T, and then using the backwards recursion, the dynamic programming algorithm, you compute V star T minus 1, then V star T minus 2, and so on down to V star of 0. And then from these you compute pi star, T and so on. Right? And so one sort of, there's not a huge difference, but one minor difference between this and the infinite horizon discounted case is that by running this recursion once, you now have exactly the right value function. So this just computes the right value function rather than merely converging asymptotically. This just gives you the right value function with one pass. Okay. All right, cool. Any questions about? Yeah.
This computation is simpler than, shorter than the value iteration itself, right?
Let's see. This computation is much shorter than value iteration itself. Sort of yes and no. It depends on how large capital T is.
My question is like for the normal MDP, could you sort of assume a capital T and then use this for that case?
I see, right. So for the normal MDP, can you assume capital T and then assume this? So it actually turns out that, So it actually turns out, I'll say, let me just, it's a great question. Let me just answer this in a slightly hand-wavy way. So it actually turns out that for a discounted infinite horizon MDP, we have some discount factor gamma. And so what you can do is, you can say, well, after T time steps, right, gamma to the T will be really small. It'll be like 0.0001 or something. And so I don't really care what happens after that many time steps because the rewards are multiplied by gamma to the T after that. I don't really care. So you can ask, can I take my infinite horizon discounted MDP and approximate that with a finite horizon MDP where the number of time steps t is chosen so that this holds true. So it turns out you can do that, but then you end up with some value for t, right? You can solve for t so that this holds true. It turns out you can prove that if you took the original value iteration algorithm, and if you run the original value iteration algorithm, the version for discounted MDPs, if you run that for this same number of time steps, you will end up with an approximation to the value function that is about this close, up to some small constant factors. And so to do that, you end up with roughly the same amount of computation anyway. And then you might actually end up with a non-stationary policy, which is more expensive to keep around, right? Because you need to keep around a different policy for every time step, which is not as nice as if you had the stationary policy, the same policy for all time steps. So, yeah. So there are other reasons where sometimes you might take an infinite horizon discounted problem and approximate to a finite horizon problem, but this particular reason is usually not the one. So, yeah, hope that makes sense. Any questions? Let's see. Oh, yeah. All right. Is there a gamma in this? So let's see. If you want, you can actually change the definition of an MDP and use a finite horizon discounted MDP. And if you want, you can do that. You can actually, come in and put a gamma there. Right, and use discounting in the finite horizon MDP. It turns out that usually, for most problems that people deal with, you either use discounting or you use finite horizon. And it's sort of been less common to do both, but you can certainly do so as well. It turns out one of the nice things about discounting is that it makes sure your value function is finite. It's just algorithmically or mathematically. One of the reasons to use discounting is because you're multiplying your rewards by this exponentially or by this geometrically decaying series, it ensures that the value function is always finite. There's little nice mathematical properties when you do discounting. So when you have a finite horizon anyway, then the value function is also guaranteed to be finite. And with that, you don't have to use discounting. But if you want, you can actually discount as well.
Right.
Yes, you're right. Yeah, and if you want, you can redefine the reward function to build gamma into the reward function, since we have non-stationary rewards as well. Okay, cool. Okay, so that was finite horizon MDPs. What I want to do now is actually use both of these ideas, use state action rewards and use finite horizon MDPs to describe a special case of MDPs, to describe actually a very special case of MDPs that makes very strong assumptions about the problem. But these assumptions are reasonable for many systems, and with these assumptions, we will come up with, I think, a very nice and very elegant algorithm for solving even very large MDPs. Let me find my... Okay, so... So, let's talk about linear quadratic regulation. So, let's see. Right. Oh, and we just talked about dynamic programming for finite horizon MDP. So just remember that algorithm, because when I come back to talk about an algorithm for solving LQR problems, I'm actually going to use exactly that dynamic programming algorithm that you just saw for finite horizon MDP. So we're using that exactly that algorithm again. So just remember that for now. So let's talk about LQR. So I want to take these ideas and apply them to MDPs with continuous state spaces and maybe even continuous action spaces. And so, to specify an MDP, right, I need to give you this 5-tuple of states, actions, transition probabilities, the time horizon, the reward. And I'm going to use a finite horizon, capital T, rather than discounting. So in LQR problems, I'm going to sort of assume the following. I'm going to assume that the state space is n-dimensional, is Rn. And I'm going to assume also a continuous set of actions. So the actions lie in Rd. To specify the state transition probabilities, PSA, I need to tell you what the distribution of the next state is given the current state and the current action. And so we actually saw a little bit of this in the last lecture, but I'm going to assume that the next state, st plus 1, is going to be a linear function of the previous state, right, ast plus bat plus wt, oh, excuse me, I meant to subscript that. Right, where where Wt is, say, Gaussian noise with mean 0 and some covariance given by sigma W. Okay, and I've subscripted A and B here with subscripts T to show that these matrices can change over time, and so this would be non-stationary dynamics. And as a point of notation, unfortunately, sort of compiling ideas from multiple literatures, and so sort of unfortunate that capital A denotes both the set of actions as well as a matrix. When you see me write A later on, A will usually be used to denote a matrix rather than a set of actions. So I'm sorry about having the overload notation again, but unfortunately, the notational conventions sort of when you have research ideas in multiple research communities often share the same symbol. And so, okay, and so just to be concrete, AT is a matrix that's n by n, and these BTs are matrices that are n by d. And just to be completely clear, right, the matrices A and B I'm going to assume are fixed and known in advance. Okay, so I'm going to give you the matrices A and B. I'm going to give you sigma W, and your job is to find a good policy for this MDP. Okay, so this is so in other words, this is my specification of the state transition probabilities. Looking ahead, it actually turns out, we see this later, it actually turns out this noise term is not very important. Right, so it actually turns out that the treatment of the noise term is actually not very important. And it actually turns out, and we'll see this later, we can pretty much ignore the noise term and get and we'll still do fine. We'll see this later, but this is just a warning that in the sequel, and what I'll do later, I might be slightly sloppy in my treatment of the noise term, because it turns out in this very special case to be unimportant. Let's see. Then the last thing I have to specify is I have some horizon time, and then I also have some reward function. And for LQR control, I'm going to assume that the reward function can be written as this. Right, where UT is a matrix that's n by n, and VT is a matrix that's d by d. And I'll assume that UT is and VT are both positive semi-definite, are both PSD. Okay, so the fact that UT and VT are both positive semi-definite matrices, that implies that, right, ST transpose UT ST must be greater than 0, and similarly AT transpose VT AT must be greater than 0, and so this implies that your rewards are always negative. Okay? So there's a somewhat depressing MDP in which there are only costs and no positive rewards, right? Because of the minus sign there. So cool. Cool. So as a concrete example of how you might want to apply this, you see my helicopter videos, right? So one thing is, for example, suppose you have a helicopter and you want the state st to be as close to 0 as possible. Then you might choose ut to be equal to the identity matrix, and this will make R of st at be equal to, st transpose st, right? But that's just, well, yeah, I'll just write that down. St transpose st, right? Which is just the squared norm of that, minus the negative of the squared norm of your state vector. And so this would be penalizing your system quadratically for having a state that's far from 0, assuming that 0 is the origin state. So if it goes to make a helicopter hover around the state 0, then you might choose this sort of reward function. Turns out it's also fairly common practice to choose a cost for the action. So suppose I choose Vt to be equal to the identity matrix, and I get minus At transpose At here, and then I have minus the norm of the actions as well. And including a quadratic cost for actions is also a fairly common thing to do. And in practice, this tends to have the effect of discouraging your system from jerking the controls around. It discourages making very huge control commands. Often adding a term like this reward function often makes many systems behave better. And of course, you can choose different values with different values on the diagonal to give different state variables different weights and so on. Okay, so lots of possible choices for U and V, but this is one example. Okay, so so for the next few steps, I'm going to write out things. I'm going to derive things for the general case of non-stationary dynamics. I'm going to, as I write out more math and more equations for LQR, I'm going to try to write it out for the fully general case of time-varying dynamics and time-varying reward function. So non-stationary dynamics and non-stationary reward function. But for the purposes of sort of understanding this material, you might want to think of this ignoring many of the subscripts in terms of t. So, for example, so concretely, just for the sake of understanding this material, you might want to mentally assume that there is some fixed matrix A, so that A is equal to A1 equals A2 equals A3 and so on. And similarly, that there's some matrix B. Okay, so I write it out for the fully general non-stationary case, but you might just want to ignore many of the time subscripts and just imagine the stationary case for now. So let's see, right? And it'll actually be only quite a bit later when I talk about an extension of this called differential dynamic programming. They'll actually use the non-stationarity to very powerful effect for a specific algorithm. But for most of what we're about to do, you can just pretend the MDP is stationary. Okay, so before I talk about models, let me just say a couple of words about how you would go about coming up with a linear model. So the key assumption in this model is that the dynamics are linear. You also have the assumption that the reward function is quadratic, but let's talk about the assumption that the dynamics are linear, right? So we assume that st plus 1 equals ast plus BAT. Maybe time varying, maybe stationary. Let me just write stationary for now. So how do you get models like this? Well, we actually saw one example of this already in the previous lecture. If you have, say, an inverted pendulum system, and you want to model the inverted pendulum using a linear model like this, maybe plus noise. I'm not going to write that down. One thing you could do is run your inverted pendulum. Right, starts off in some state S0, takes some action A0, have it get to some state S1, take action A1, and so on, get to some state ST. I'll index this 1 to denote that this is my first trial. And then you can repeat this a bunch of times. You can repeat this m times, right, of just executing actions on your physical robot. And it could be a robot, it could be a chemical plant, it could be whatever, of trying out different actions in your system and watching, try different actions in your system and watch what states it gets to. And then to fit a model, to fit a linear model to your data, right, you can choose the parameters A and B that minimize the sort of quadratic error term. Right? So this says, how well does AST plus BAT predict ST plus 1? So you can minimize this sort of quadratic penalty term, and this would be one reasonable way to estimate the parameters of a linear dynamical system for like a physical robot or a physical chemical plant or whatever they may have. Another way to come up with a linear model, let's get rid of this. Another way to come up with a linear model for a system that you might want to control is to take a nonlinear model and to linearize it. So let me say what I mean by that. So you can linearize a nonlinear model. Okay. So concretely, let's say you have some nonlinear model that expresses st plus 1 as some function of st and at. In the example that we saw in the previous lecture, I said for the inverted pendulum, right, there was that problem with the little cart and the pole, right? By referring to laws of physics, or actually by downloading off-the-shelf software for doing physics simulations, right? So if you haven't seen software before, you can just Google online. You can easily find many open source packages for simulating the physics of simple devices like these. You pretty much download the software, type in the specs, type in the specifications of your robot, and it'll simulate the physics for you. There are lots of open source software packages like that. You just download now. But something like that, you can now build a physics simulator that predicts, the state as a function of the previous state and the previous action. Right? So you actually come up with some function that says that, right, the state to the next time in this full vector will be some function of the current state and the current action, where the action in this case is just a real number saying how hard do you accelerate to the left or right. And then you can take this nonlinear model, right, and I actually wrote down an example of a model in the last lecture, but in general, f will be some nonlinear function, and you can then approximate to a linear function. So what I mean by linearize is the following. So here's just a cartoon. I'll write down the math in a second. Let's say the horizontal axis is the input state st, and the output state st plus 1 is like so. So whatever, right? So here's the function f. So the next state st plus 1 will be some function of the previous state st, maybe a previous state st and the action at. And so to linearize this model, what you would do is you choose a point. Let me call this s bar t. And then you would take the derivative of this function and basically for the tangent straight line to that function. And so this allows you to express the next state st plus 1. You can approximate the next state st plus 1 as this linear function of the previous state st. Right? Though to make this cartoon really right, the horizontal axis here is really a state-action pair. And you're linearizing around. So this is just a cartoon. So the horizontal axis represents the input state and the input action. So Just to write this out in math, well, I'll write out the simple case first and the fully general one in a second. Suppose the horizontal axis was only the state. So let's pretend there are no actions in NDP now. If st plus 1 is just some function of st, then that linear function I drew would be that st plus 1, we're approximating as f prime evaluated at some point s bar t times st minus s bar t plus f of s bar t, right? And so, with this, you've expressed st plus 1 as a linear function of st. And just note that s bar t is a constant, right? It's not a variable. So, does that make sense? So s bar t is a constant. F prime of s bar t is the gradient of the function f at the point s bar t. And this is really just the equation of that linear function. And so you can then convert this to A and B matrices. Okay. Let's see. Right. So just jumping back one board. Just point out one other thing. Suppose I look at the straight line, and I ask, how well does a straight line approximate my function f, my original simulator, my original function f? Then you sort of notice that in this neighborhood, right, in the neighborhood of s bar, is a pretty good approximation. It's fairly close. But then as you move further away, maybe far off to the left here, it becomes a pretty terrible approximation. And so when you linearize the dynamics, when you linearize a nonlinear model to apply LQR, one of the parameters you have to choose will be the point around which to linearize your nonlinear model. And so if you expect your system, if you expect your inverted pendulum system to spend most of its time in the vicinity of this state, then it'd be reasonable to linearize around this state, because that means that the linear approximation will be a good approximation, usually for the states that you expect the system to spend most of its time. Right. If conversely you expect the system to spend most of its time at states far to the left, then this would be a terrible location to linearize. And so one rule of thumb is to choose a position to linearize according to where you expect the system to spend most of its time, so that the linear approximation will tend to be good, will tend to be an accurate approximation in the vicinity of the states that you actually expect to see the most often. And just to be clear, this is about choosing the point S bar, A bar, that we'll use to come up with a linear function that will pretend is a good approximation to my original nonlinear function f. Okay. Let's see. Right. Right. And so, for example, like the inverted pendulum problem, for this problem, if you expect to do pretty well in this problem, then you would expect the state, to often be near the zero state, right? If x equals 0 corresponds to x being in the center of the railway track that the inverted pendulum count lives on. If you expect to do fairly well, you expect the pole to mostly be upright. It's depending on whether upright is 0 degrees or 9 degrees, I guess. But so you choose whatever state corresponds to having the pole upright at zero velocity and the count, near zero velocity and in the middle of the track. So you would usually choose that as a state to linearize your inverted pendulum dynamics around, since that's the state, that's the region where you might want your approximation to be good. So I wrote this down. So coming back to this formula, I wrote this down for the special case of a 1D state variable, and if there are no actions. The general formula for the linearization approximation is that st plus 1 will approximate as f of s bar t, a bar t, plus bar t. Okay, where these upside down triangles are our usual symbol for taking the derivative of f with respect to the vector value first argument or the vector value second argument. And so by choosing an appropriate state s bar t, a bar t to linearize around, you've now expressed st plus 1, this thing, as a linear function of the current state and the current action at. Right? And again, these things, s bar t is a constant that you choose ahead of time. Right? And the same for a bar t. All right, cool. And lastly, having linearized this thing, you can then convert it to matrices like that. Right? So the st plus 1 is now a linear function of st and at. Okay. Any questions about this? Okay, cool. We think, yeah. So just one tiny detail is that it's really not a huge deal. Is that this thing below is technically an affine function that there may actually be a constant offset, that there may actually be an extra constant there. But this is not a difficult generalization of a linear dynamical system definition. And one way to deal with that constant is actually to do something like take your definition for the state. Let's say x dot theta theta dot. And you can then augment your state vector to have an extra intercept term 1. And with the intercept term 1 and working out the A matrix, you can then take care of this extra constant C as well. So you can deal with this thing being, technically it's an affine function because it's extra offset rather than a linear function. But this is just a little bit of bookkeeping that you can work out for yourself and shouldn't be a huge deal. All right. So 20 minutes left. Okay, cool. So to summarize, let's have this up. You can learn a model, or you can take a nonlinear model. Your nonlinear model can be a physics model or a nonlinear model that you learned, and linearize it. And now we've posed an LQR problem in which we have specification of the MDP in which the states are in Rn, the actions are in Rd, and the state transition probabilities are given by this sort of linear equation, right? St plus 1 equals ATST plus BTAT. And our rewards are going to be these quadratic functions, right? And so the specification of the MDP means that we know the A matrices, the B matrices, the U matrices, and the V matrices. And our goal is to come up with a policy to maximize our finite horizon sum of rewards. So our goal is to come up with a policy so as to maximize the expected value of this finite horizon sum of rewards. Okay. So our approach to solving this problem will be exactly that finite horizon dynamic programming algorithm that we worked out a little earlier in this lecture. In particular, my strategy for finding the optimal policy will be to first find V star of t, right, for capital T, and then I'll apply backward recursion to find V star of t minus 1, V star of t minus 2, and so on. Okay, so let's see. In the dynamic programming algorithm we worked out, V star subscript t of the state st, this is max overall actions you might take at that time of R of st at, right? And again, just for the sake of understanding this material, you can probably pretend the rewards and the dynamics are actually stationary. I'll write out all these superscripts, all the time indices, but probably just ignore them when you're reading this for the first time. And so this, let's see, the reward is equal to max over AT of minus right? I hope this isn't confusing. The superscript t's denote transposes. The lowercase t denote the time index capital T. So that's just a definition of my negative quadratic reward. And so, well, this is clearly maximized as minus st transpose ut st. You know, because that last term is you know, this is greater than or equal to 0 because of my assumption that Vt is positive semi-definite. And so the best action to take of the loss time step is just the action 0. And so pi star subscript t of st is equal to the argmax over actions of that same thing. It's just 0. Okay. So by choosing the 0 action, AT transpose VT AT becomes 0, and that's how this reward is maximized. So boards. Is there a question, or is something illegible? Is that okay? Okay. So now let's do the dynamic programming step, where my goal is, you know, given Vt plus 1, right? I want to compute Vt. I guess given V star t plus 1, I want to compute V star of t. So this is the dynamic programming step. So the DP step that I wrote down previously was this, right? So for the finite state case, I wrote down the following. Shoot. Okay, right. So this is exactly the equation I wrote down previously, and this is what I wrote down for finite states, where you have these discrete state transition probabilities, and we could sum over this discrete set of states. Now we're in a continuous or infinite state again, so this sum over state should actually become an integral. But let me actually skip the integral step. Let me just go ahead and write this last term here as an expectation. So this is going to be max over actions AT of plus, and then this becomes an expectation over the random next state st plus 1, drawn from state transition probabilities given by P of stat of v star t plus 1 st plus 1. Okay, so this is the same equation written down as an expectation. And so what I need to do is, given a representation for v star t plus 1, I need to find v star of t. So it turns out that LQR has the following useful property. It turns out that each of these value functions can be represented as a quadratic function. So concretely, let's suppose that v star t plus 1, right? Suppose that this can be expressed as a quadratic function written like so, where the matrix phi t plus 1 is an n by n matrix, and psi t plus 1 is just a real number. So in other words, suppose v star t plus 1 is, this sort of quadratic function. Suppose v star t plus 1 is a quadratic function of the state st plus 1. We can then show that when you do one dynamic programming step, excuse me, when you plug this definition of v star t plus 1 into that dynamic programming step in the equation I had just now, you can show that you will get that v star t as well will also be a quadratic function, of the same form. For some appropriate, right? For some appropriate matrix phi t and some appropriate real number psi of t. And so what you can do is start off the recursion with, well, does this make sense? So what you can do is start off the recursion as follows. So previously we worked out that v star capital T, right? We said that this is minus st transpose ut st. And so we have that phi of capital T is equal to minus ut, and psi of capital T is equal to 0. And now v star t of st is equal to st transpose phi of t st plus psi of t. And so you can start out the recursion this way, with phi of t equals minus ut and psi t equals 0. And we then work out what the recursion is. And I won't actually do the full derivation. It's mainly algebra, and you all know how to do math by now. You've actually done this sort of Gaussian expectation math a lot in your homeworks by now. So I won't do the full derivation. I'll just outline the sort of one-ish key step. So the dynamic programming step, we have v star st, right, is equal to max over actions at of the immediate reward right? So this was R of SA from my equation in the dynamic programming step. Then plus an expected value over the random next state st plus 1 drawn from a Gaussian distribution with mean at st plus bt at and covariance sigma w, right? So what this is really my specification for pf st at. This is my state transition distribution, right, in the LQR setting. This is my state transition distribution for if I take action at in the state st. And then my next state is, distributed Gaussian with mean ATST plus BTAT and covariance sigma W. And then of this thing. Right. And this, of course, is just V star t plus 1 of st plus 1. Okay? Hope this makes sense. Right. So this is just, taking that equation I had previously in the dynamic programming step and said that V star of t st equals max over actions of the immediate reward plus an expected value over the next state of V star of the next state with the clock advanced by 1. And so I've just plugged in all the definitions of the reward, of the state transition distribution, and of the value function. Actually, could you raise your hand if this makes sense? Cool. And so if you write this out, you expand the expectation. I know you've done this many times by now, so I won't do it. This whole thing on the right-hand side simplifies to a big quadratic function of the action at. So this whole thing, right, simplifies to a big quadratic function of the action at. And so we want to maximize this with respect to the actions at. And so to maximize a big quadratic function, you just take the derivatives of the function with respect to the action at, set the derivative equal to 0, and then you've maximized the right-hand side with respect to the action at. And it turns out, and I'm just going to write this expression down for completeness. You can rederive it yourself anytime, right? So it turns out if you actually maximize that thing on the right-hand side as a function of the actions at, you find that the optimal action to take at is going to be that. Times st. Okay, and don't worry about this expression. You can get it from the notes, or you can rederive it yourself. But the key thing to note is that the optimal action at is going to be some big matrix. I'm going to call this thing lt times st. Okay. And in other words, the optimal action to take in a given state is going to be some linear function of the state st. So having done the dynamic programming, you remember also when we worked out the dynamic programming algorithm for finite horizon MDPs, we said that the way you compute the optimal policy pi star of t of st, right? This is always the argmax of the same thing, right? Argmax over actions at of the same thing, right? STAT plus expected value of a state drawn from P ST AT B star T plus 1 ST plus 1. Right. I mean, this thing on the right hand side is always the same thing as the thing we maximized to do the dynamic programming backup. And so what this means is that, well, I said that this is the value of AT that maximizes this. So what this means is the optimal action to take from a state ST is actually equal to LT times ST. Okay. And what was shown is that when you're in some state ST, the optimal action for that state is going to be some matrix LT, which you can compute, times the state ST. In other words, the optimal action is actually a linear function of the state. And I was just going to point out, this is not a function approximation thing, right? So this is not about, this is what we did not do. We did not say, let's find the optimal linear policy, or we didn't say, let's look at the optimal policy and then we'll fit the straight line to the optimal policy. This is not about approximating the optimal policy with a straight line. This derivation is saying that the optimal policy is a straight line. The optimal action is a function, is a linear function of the current state. Well, moreover, when you take this, so you worked out that this is the value for AT that maximizes this thing on the right-hand side. So you can take this and plug it back in to do the dynamic programming recursion, and what you find is that so you can take AT, plug it back in to do the maximization to actually get you, this formula, right, for V star TST. And so you find that it will indeed be a quadratic function like this of the following form, where And I'll just write out the equations for the sake of completeness, but again, don't worry too much about their forms. And you can derive this yourself. Transpose there. Minus and okay. So just to summarize, really don't worry too much about the forms of these equations. Just to summarize, what we've done is we've written down a recursion that expresses phi t and psi t as a function of phi t plus 1 and psi t plus 1. And so this allows you to compute the optimal value function for when the clock is at time t, time lowercase t, as a function of the optimal value function for when the clock is at time t plus 1. And so, to summarize, here's the LQG, here's the finite horizon. Oh, excuse me. And actually, just to give this equation a name as well, this recursion in terms of the phi t's, this is called the discrete time Riccati equation. It's basically the recursion that gives you, phi t in terms of phi t plus 1. Okay. So, to summarize, our algorithm for finding the exact solution to finite horizon LQR problems is as follows. We initialize phi t to be equal to minus qt, to minus ut, and psi t to be equal to 0. And then, recursively calculate phi t and psi t as a function of phi t plus 1 and psi t plus 1, right, with the discrete time. Actually, excuse me. Right, so recursively calculate phi t and psi t using, as a function of phi t plus 1 and psi t plus 1, as I showed, using the sort of discrete time Riccati equation. And so you do this for t equals t minus 1, t minus 2, and so on down to time 0. Then you compute LT, as a function of, actually, was it phi t or phi t plus 1? Phi t plus 1, I think. Right. As a function of phi t plus 1 and psi t plus 1. There's actually a function only of phi t plus 1. You don't really need psi t plus 1. And now you have your optimal policy. So having computed the LTs, you now have that the optimal action to take in the state ST is just given by this linear equation. Okay. Let's check how much time I have left. Well, those. Well, let me just say one last thing about this before I close. Yeah. now? Maybe I'll do it next week. I think I'll do it in the next lectures instead. Okay. So this actually turns out there's one very cool property of this that is kind of subtle, but I'll find that out in the next lecture. Are there questions about this before we close for today then? So the very cool thing about the solution of discrete time LQR problems, finite horizon LQR problems, is that this is a problem with an infinite state, with a continuous state, right? But nonetheless, under the assumptions we made, you can prove that the value function is a quadratic function of the state. And therefore, just by computing these matrices phi t and the row numbers psi t, you can actually exactly represent the value function, even for these sort of infinitely large state spaces, even for continuous state spaces. And so the computation of this algorithm scales only like the cube, scales only polynomially in terms of the number of state variables. Whereas in the recursive dimensionality problems, right, with discretization, we had algorithms that would scale exponentially in the dimension of the problem. Whereas LQR scales only like the cube of the dimension of the problem. And so this is easily applied even to problems with very large state spaces. And so we actually often apply variations of this algorithm to some subset, to some significant subset of the things we do on our autonomous helicopter, which has high dimensional state spaces, so like 12 or higher dimensions. And this has worked very well for that. Okay, so it turns out there are even more things you can do with this, and I'll continue with that in the next lecture. So let's close for today then.